The product of sums is greater than or equal to the sum of products squared. And for more information about this inequality, you should check the videos linked in the description. But today, I want to show you a special case of the Cauchy-Schwarz inequality. So let me show you two sets. So let's let the first set be a1 over the square root of b1, a2 over the square root of b2, a3 over the square root of b3, so on up to an over the square root of bn. And now let's let the second set be the square root of b1, the square root of b2, the square root of b3, all the way to the square root of bn. So we get that a1 squared over b1 plus a2 squared over b2 all the way to an squared over bn times b1 plus b2 all the way to bn. This is greater than or equal to the product of each of these terms taken and then all squared. So we get a1 plus a2 plus a3 all the way to an all squared. But now what happens if we divide both sides by b1 plus b2 all the way to bn? Well, then we would get that a1 squared over b1 plus a2 squared over b2 plus a3 squared over b3 all the way to an squared over bn. This is all greater than or equal to a1 plus a2 plus a3 all the way to an all squared over b1 plus b2 plus b3 all the way to bn. Now this inequality right here is known as Titu's lemma. So now let's change up our inequality at the top once again. So now we have our special case of Cauchy-Schwarz here on the board. So I'm going to show you an example where this is useful. So how would you prove 2 over a plus b plus 2 over a plus c plus 2 over b plus c is greater than or equal to 9 over a plus b plus c? Well, we don't see any perfect squares in the numerators on this side, but we do see a perfect square on this side, so it still does suggest that we should use Titu's lemma. But notice that our perfect squares don't need to be perfect. 2 is still equal to root 2 squared, and so we know that 2 over a plus b plus 2 over a plus c plus 2 over b plus c is greater than or equal to root 2 plus root 2 plus root 2 all squared over a plus b plus a plus c plus b plus c, which is equal to 2 times a plus b plus c. And since we know that root 2 plus root 2 plus root 2 is equal to 3 root 2, we can then square this to get 9 times 2. And then we can square this to get 18 over 2 times a plus b plus c. We can then divide by 2 to get 9 over a plus b plus c. And so we have proven this inequality and we are done. Alright, and now let's get into some problems. Alright, and now our first problem is above me. So this problem is also another IMO problem, but I promise you this one's going to be a lot easier than the one from last time, especially now that we have our new inequality. So the first thing is we have to change up the terms a little bit. So 1 over a cubed times b plus c. We can rewrite this as 1 over a squared over a times b plus c. This is also equal to 1 over a squared times ab plus ac. So similarly, we can apply the same logic to 1 over b cubed times a plus c and 1 over c cubed times a plus b. These two are both equal to 1 over b squared over ab plus bc, and this is equal to 1 over c squared over ac plus bc. So the important thing about Titu's lemma is looking for squares in the numerator, because if we have squares in the numerators, then we can set up an inequality such that the left-hand side is greater than or equal to the right-hand side over here. So now we have 1 over a squared over ab plus ac plus 1 over b squared over ab plus bc plus 1 over c squared over ac plus bc. And so this is greater than or equal to 1 over a plus 1 over b plus 1 over c all squared divided by ab plus ac plus ab plus bc plus ac plus bc. Now adding all these terms together, we get 2 times ab plus bc plus ac. So now let's consider 1 over a plus 1 over b plus 1 over c. Now we know that since a, b, c is equal to 1, we can divide both sides here by a to get that bc is equal to 1 over a. So we get bc, and so bc is equal to 1 over a. So we apply the same logic to 1 over b. We can divide both sides by b to get that ac is equal to 1 over b. So then we add ac, and 1 over c is equal to ab. So ab is equal to 1 over c, ab is equal to 1 over c. So then this part of the right hand side here then becomes ab plus bc plus ac all squared over 2 times ab plus bc plus ac. And now we can divide ab plus bc plus ac to get that this is equal to ab plus bc plus ac all divided by 2. And now, since we know that 1 over a squared over ab plus ac plus 1 over b squared over ab plus bc plus 1 over c squared over ac plus bc is greater than or equal to ab plus bc plus ac over 2, if we can prove that this is greater than or equal to 3 over 2, and so proving that ab plus bc plus ac over 2 is greater than or equal to 3 over 2 will suffice to solve this problem. And so let's move this part of the inequality to the top. So the first thing that we want to do here is multiply both sides by 2. So we get ab plus bc plus ac is greater than or equal to 3. So now we can apply AMGM to this equation. ab plus bc plus ac over 3 is greater than or equal to the cube roots of ab times bc times ac, or ABC all squared. And now we know that from the problem, ABC is equal to 1. So this then becomes the cube roots of 1, which is also equal to 1. Now multiplying both sides by 3, we have now proven that AB plus BC plus AC is greater than or equal to 3. And so this is true. And now we are done. So we have solved this problem much faster using Titu's lemma because we already know which special case of Cauchy-Schwarz we are looking for. And because we see squares in the numerator, we can use this special case of Cauchy-Schwarz to solve this problem much faster. Alright, and now let's move on to the next problem. Alright, and now our next problem is right here. And so the first thing we have to do is split the numerators. And so we have a cubed over 5a plus b plus 3b cubed over 5a plus b, plus b cubed over 5b plus c, plus 3c cubed over 5b plus c, plus c cubed over 5c plus a, plus 3a cubed over 5c plus a. So we don't see any perfect squares at first, but what we can do is we can multiply this term, and this term by a over a, b over b, and c over c, and this term, and this term by 3a over 3a, 3b over 3b, and 3c over 3c. And so multiplying, this is then equal to a to the 4 over 5a squared plus ab plus 9b to the 4 over 15ab plus 3b squared plus b to the 4 over 5b squared plus bc plus 9c to the 4 over 15bc plus 3c squared plus c to the 4 over 5c squared plus ac plus 9a to the 4 over 15ac plus 3a squared. So now we can rewrite this as two cyclic sums. This is then equal to the cyclic sum of a to the power of 4 over 5a squared plus ab plus the cyclic sum of 9a to the 4 over 15ac plus 3a squared, such that the set of variables being cycled through is a, b, c. So we know that a to the power of 4 is equal to a squared squared, and 9a to the power of 4 is equal to 3a squared squared. And so this is greater than or equal to 4a squared plus 4b squared plus 4c squared all squared over 8 times a squared plus b squared plus c squared plus 16ab plus bc plus ac. So now let me show that a squared plus b squared plus c squared is greater than or equal to ab plus bc plus ac. So we can multiply both sides of the inequality by 2 to get 2a squared plus 2b squared plus 2c squared is greater than or equal to 2ab plus 2bc plus 2ac. Then we can move these terms to the other side. So we get 2a squared minus 2ab plus 2b squared minus 2bc plus 2c squared minus 2ac is greater than or equal to 0. So now we can start factoring these terms. So we get that a minus b squared plus b minus c squared plus a minus c squared is greater than or equal to 0. And since all real squares must be positive, this statement is true, and so we have proven this. So then it is true that 16 times ab plus bc plus ac is lesser than or equal to 16 times a squared plus b squared plus c squared. And so we now know that this is greater than or equal to 16 times a squared plus b squared plus c squared all squared divided by 24 times a squared plus b squared plus c squared. Now I'm going to move this all to the top and continue solving. Alright, so now we have our inequality up here, but then we can simplify 16 over 24 to get that this is equal to 2 over 3 times a squared plus b squared plus c squared squared divided by a squared plus b squared plus c squared is equal to a squared plus b squared plus c squared. And because it suffices to show that this is greater than or equal to this, we have now solved the problem and we are done. Alright, thanks for watching. Hopefully you enjoyed. If you haven't watched my other Cauchy-Schwarz videos, I highly suggest that you go and check them out. And hopefully, I'll see you next time.